Hello everyone. This video covers sections 8.2 and 8.3. So let's start with 8.2. Just to refresh your memory, in chapter 1, we solved first order linear differential equations. So the whole chapter was about this. So now in chapter A, we're going to do second order and higher than that, but mostly second order differential equations, but they are still linear. Okay? And we clarify what linear was at the beginning of chapter 1, so you need to refresh your memory. Just refer back to the first lecture we actually did. In this section, we're going to focus specifically on second order differential equations, and this will be the general form. So it's going to look like this. So this will be the general. So this it will be linear, and in this case, this one is second order. Remember, the second order means the highest derivative is 2. Okay. All right. So now, what we're going to do right now, this is technically what we're trying to solve. And now you need two initial conditions because you have two derivatives. By the way, the independent variable could be x or could be t. Most of the time we will use x, but if you replace this by t, it doesn't matter. Now we're gonna make a big assumption here, and the assumption is going to be that this function f is gonna be linear. But remember what it means to be linear for differential equations. It means that the function in here only depends on x, it doesn't depend on y, and that we don't have any powers or exponents or roots or anything in y or y prime or so forth. Okay, and also that this function depends on x only. Now if we rearrange the terms, so we will end up with this. And by rearrange, I mean this. We move this to this side and this to this side. Remember that this, by definition, is the second derivative. Remember that this is just another name for y double prime. So therefore, if we rearrange this, do a little bit of algebra, we end up with something like this. And this is the equation we're going to focus, at least for the beginning of the section. Actually, for most of this chapter, we're going to assume that p of x and q of x are actually constants. So they will not even depend on x. And the first case we're going to do is going to be where the value for f of x is equals to 0. So this is what homogeneous means. Homogeneous will mean that this is equals to 0. So in 8.1, in 8.2, we're gonna see how we solve these equations where this is equals to 0, which you will see is actually pretty easy. Then in 8.3, we're gonna solve this when this is not 0, and that's gonna make problems a little more tricky. So the general form, if we assume that these are constants, is gonna look like this. So this is a general homogeneous second order differential equation that is linear. And like I say already, A, B, and C are gonna be constants. All right, so for this section, we're gonna assume, and this is one of the most important assumptions, so we're gonna assume, which is gonna turn out to be the right assumption, that the solution is gonna look like this, where R is also a constant. Okay, so we'll assume the solution is of this form. Therefore, y prime will be r e to the rx, and y double prime will be r squared e to the rx. Now let's call this equation star, which is the one we're trying to solve. If we plug in these three into the star equation, from here we'll get the following. We will have the a r squared e to the rx plus b r e to the rx plus c e to the rx is equals to 0. Notice that clearly from here you can factor the e to the rx. So this will give you a r squared plus br plus c is equals to 0. Now again, from basic algebra, this means that e to the rx has to be 0, or ar squared plus br plus c has to equal to 0. But remember, this one is never equals to 0. Why? Okay, so you should answer the question by yourself. You should know that, but for now, just need to know that this is never 0. So therefore, the only hope you have is that this is equals to 0. And this part is going to be called actually the characteristic equation. So characteristic equation. And this is going to be the basis to everything we're going to do in chapter A, or at least at the beginning. Now remember that from here, and this is from, again, basic algebra, actually from the quadratic equation, there is three cases. The first case is you can have two real solutions to this. If you look to the quadratic equation, and the two real solutions, for lack of a better name, we will just call it R1 and R2. The other thing that can happen is that you have two complex solutions. And remember, the complex solutions look like a plus or minus bi. And the last thing that can happen is that you have one repeated solution. And again, this is not new. This is something that you learn in elementary algebra. And these are the three choices if you use the quadratic formula. Okay. So therefore, in general, the solution that we're gonna find, which is technically, this is called a homogeneous solution, because remember that this part is equals to 0. So the solution is going to be y is equals to c1 e to the r1x plus c2 e to the r2x, where r1 and r2 are either too real, too complex, or is one repeated solution. So this is going to be the goal. So this is what we're trying to find. You will see very soon, excuse me, that actually to solve second order differential equations, at least at the beginning, is actually easier the first order linear differential equations. Then it gets a little more tricky, but at the beginning it's actually a lot easier, like you will see in a few minutes. Now the reason why we have two constants is because the equation has two derivatives. It is going to have three derivatives. You will need C1, C2, C3, and so forth. All right, so now we're going to do an example where this happened, then where this happens, and then where this happens. Okay, so let's try this example. So the first thing you have to do all the time when you're dealing with these equations is to find the characteristic equation. And like you saw from the last page, the characteristic equation is just going to be AR squared plus BR plus C is equal to 0. So in this case, the characteristic equation is going to be R squared plus 7R plus 10. And then just factor this the same way that you factor this in algebra. So this is R plus 5 times R plus 2. So that means that the first solution is -5 and the second solution is -2. So this is the first case. So this is case 1 where you have two real solutions. So therefore the solution is going to be y of x is equals to c1 e to the minus 5x plus c2 e to the minus 2x. And if you don't have any initial conditions, that's it, because without initial conditions you cannot find c1 or c2. All right, let's try one more. So remember, first thing, characteristic equation, which will be r squared minus r minus 2 is equals to 0. Factor, so this is r minus 2, r plus 1 is equals to 0. So that means that r1 is 2 and r2 is -1. All right, so therefore the solution is y of x is equals to c1 e to the 2x plus c2 e to the minus x. So then if we apply the initial conditions, okay, so this is the only way you can find out the value for c1 and c2. So let's start with this one, y of 0 is equals to 1. So that means that 1 is equals to c1 e to the 0 plus c2 e to the 0. So from here we get this equation that c1 plus c2 is equals to 1. Now the second initial conditions requires that you have the derivative. So the first thing we need to do is find the derivative. So y prime is going to be 2c1 e to the 2x minus c2 e to the minus x. So therefore, if we plug in y prime of 0 is equals to 2, this will give us 2 is equals to 2c1 minus c2. So from here, we get a second equation, which will be 2c1 minus c2 is equals to 2. So then if you solve the system of equations, you can see that this cancel. So you have 3c1 is equals to 3. So that means c1 is equals to 1. Then if you plug that into the first equation, you have the c1 plus c2 is equals to 1. So that means that 1 plus c2 is equals to 1, which means c2 is equals to 0. So therefore the solution, okay, it will be y of x. You don't have to put the x if you don't want to, but y of x is equals to c1, which is 1, times e to the 2x plus c2, which is 0, times e to the minus x. So therefore, it's just e to the 2x. And that's it. And like I say, this is, at least for now, this is very, very, very simple. It's faster than using the integrating factor method or exact equations or any of the methods from chapter 1. Okay, so now let's look to case 2, where the solution to the characteristic equation are complex numbers. Okay, so let's say that this is the solution to some characteristic equation. Okay, any equation that will give you the solution. Okay, all right, so from here we have technically two solutions which are complex. So for lack of a better name, let's say that R1 is 2 plus 3i and R2 is 2 minus 3i. Okay, if we follow the same pattern from the last case where you had two real solutions, so therefore the answer should look like this. It should be c1 e to the 2 plus 3i x plus c2 e to the 2 minus 3i x. And this is technically correct. So this is pretty much correct. There's technically nothing wrong with this, except that this is not very, very practical because of the complex numbers. So again, this is technically okay, but not practical for what we're going to do. So instead, if we use Euler's identity, which I'll tell you what it is in a second, we're going to come up with a solution that will make our life easier. So in general, if the solution is complex, which means, let's say that you have R is equals to A plus or minus BI, the solution is going to look like this. We're going to have Y is equals to A or C1, it doesn't matter, e to the AX, sorry. Remember, you can change it to T, but we'll stick to X for now. And it will be cosine BX plus B e to the AX sine BX. So every time you have a complex solution to the characteristic equation, this is how the solution is going to look. So therefore, in our case, the solution will be y is equals to c1 e to the 2x cosine 3x plus c2 e to the 2x sine 3x. Now this is the solution we're going to use. So this is more practical, and this is the one that we will use from now on until the class is over. So this is technically equals to this, but this is the one we should use all the time. So anytime you see complex solutions to the characteristic equation, you automatically just use this formula, and that's it. Now, how is it that this is equals to this? I'm going to show you using Euler's identity why that's the that's the case. But again, if you don't want to deal with Euler's identity, you don't have to. You can just straight go to this formula. But it's a good idea to know where things come from. Now, if you remember Euler's identity from pre-calculus, from pre-calculus, e to the I theta is equals to cosine theta plus I sine theta. Therefore, that means that e to the minus I theta will be equals to cosine of minus theta plus I sine of minus theta, which is equals to cosine theta minus I sine theta. You use the identities from pre-calculus. So therefore, this means that e to the I theta plus e to the minus I theta is equals to cosine theta. It's actually equals to 2 cosine theta, right? Because this will cancel this, and cosine plus cosine will give you 2. So therefore, from here, that means that cosine theta is equals to e to the I theta plus e to the minus I theta divided by 2. Now you can use the same identity and to cancel the cosine, and you will end up with an identity for sine also. Now this is the part that I want you to see, okay? Again, you don't have to use this formula at all, but you need to see this at least once in your life. So this is what I mean. Look, if you look to this part, you can see that you have e to the I theta right here, except that this one has actual numbers, but this is what I mean. You will have e to the 3x and e to the minus 3x. So technically, e to the 3ix plus e to the minus 3ix should be equals to 2 cosine 3x, okay, using this formula right here. Or cosine 3x will be this divided by 2, but that's where the constant comes in. And you can see clearly they have e to the 2x here, which is this part. So this is the whole point of this identity, that you can combine it. If you combine these two, that will give you the cosine. And then if you do another simplification, it will give you the sine. Again, you don't have to worry about deriving the formulas. I'm just telling you how you got it. All you need to know is how to use this one right here, which we will use right now. For example, if you end up with this, let's say that r is equals to 1 plus or minus I. That means that the solution will be y is equals to c1 e to the x cosine x plus c2 e to the x sine x. That's it. Now if you have r is equals to 0 plus or minus 4i, then the solution will be y equals to c1 e to the 0 cosine 4x plus c2 e to the 0 sine 4x. And that's it. All right, so let's try one more problem where we will have complex solutions. So from here, the characteristic equation will be r squared minus 2r plus 6 is equals to 0. Now you cannot factor this, so you have to use the quadratic formula. So r will be equals to 2 plus or minus, and then this will be 4 minus 4ac divided by 2a Okay, so this is just the quadratic formula. This is actually equals to 2 plus or minus the square root of negative 20 divided by 2, and this is equals to 2 plus or minus 2 radical phi I, so here's the complex part, divided by 2, or this is just 1 plus or minus the square root of phi I. So this is A, and this is B. So therefore, if we use the general formula, then from here the solution will be y is equals to A. You can call it A or C1, it doesn't really matter. This will be now e to the x, then cosine radical phi x plus B e to the x sine radical phi x. Now you can also factor the e to the x if you want to. So it's a personal preference how you want to write this. So it is up to you. Alright, so now let's look to the last case in which you have repeated roots. Here the characteristic equation will be r squared minus 2r plus 1 is equals to 0, which will factor to r minus 1 times r minus 1. So technically here r1 is equals to 1, but r2 is equals to 1, which is exactly what we were expecting since they are for repeated solutions. Okay? Alright, so this is the issue now. So the solution cannot be like this, okay? Because if this was the case, then you can combine these two, and C1 and C2 is a constant, so you will only have one constant. So instead, when this happens, is that you're gonna multiply the second part by t or x. Okay, actually let me change this to x. Okay. So it is x, will be x. So then you multiply this one by x. So therefore the solution will be c1 e to the x plus c2x e to the x. So you just multiply by x, and this will fix the issue when you have repeated solutions. Now, if you have more than two roots, which could be the case, let's say that the characteristic equation was this, r minus 1 q is equals to 0. So and then in this case, r1 will be 1, r2 is also 1, and r3 is also 1. So in this particular case, then the solution will be y is equals to c1 e to the x plus c2 x e to the x plus c3 x squared e to the x, and so forth. Like I said at the beginning, to solve second order differential equations, at least at the beginning, it's pretty easy. Also, take into account that we only solve so far homogeneous equations where this is equals to 0. In the next section, we're going to solve equations that are not homogeneous. But if you already understand the first three methods we did so far, that's going to make life pretty easy. Remember, the goal is you find the characteristic equation, and from there you either have two real, two complex, which we had to use sine and cosine, and two repeated, which you had to multiply by something to compensate or find another solution. All right, so let's go to section 8.2. And in section 8.2, we're gonna solve the same type of differential equations that we were solving, except that this is not homogeneous anymore. So this is the difference, and this is gonna make the problem a lot longer and harder many times. And the method we're gonna use to solve the system is gonna be called undetermined coefficients. So that's why this is the main or the title of the section. Okay. All right. So the solution actually has two parts, YC and YP. Now YC, we already know how to do this. So this is the homogeneous solution that we did in section 8.1. But now we have something new which is called the particular solution. And this is where we're going to use this method to find this. So this is the part that is new. All right, so let's do an example, and you'll see that it's actually not that bad. So first, we're going to do the homogeneous part, which is this part right here. And this is exactly what we did in the last section. So first, we need the characteristic equation, which is r squared plus 3r plus 2 is equals to 0. Then we factor this, and r1 is negative 2, and r2 is negative 1, exactly like we did before. So therefore, the characteristic solution or homogeneous solution is going to be c1 e to the minus 2x plus c2 e to the minus x, which is exactly what we did before. All right, so now let's do the particular solution, which is the part that is new. For the particular, we're going to assume that the solution is going to look like this. So yp is the particular solution. It's going to be some constant e to the 3x, and we obviously pick e to the 3x because this one is e to the 3x. Then we just take derivatives, and this is the part where, depending on how this looks, this could be pretty annoying. It's not hard, but it will be annoying and tedious. So y prime is 3a e to the 3x, and y double prime is equals to 9a e to the 3x. Okay. Then we just substitute in here. So we're going to plug in. So if we do that, we will end up with 9a e to the 3x plus 3 times 3a e to the 3x, and then plus 2 e to the 2a e to the 3x, and then they should equals to e to the 3x. So this is what should be. So you just need to make sure that the coefficients match this one. That's why it's called undetermined coefficients. So you simplify this, you have 9a e to the 3x plus 9a e to the 3x plus 2a e to the 3x is equals to e to the 3x. So notice that you can factor the e to the 3x on the left side, and this will give you 9 plus 9 plus 2, so that will be 20a. And on the other side, you have e to the 3x. So obviously, if you want this to equals to this, so if we want this, you have no choice, but that means that 20a has to equals to 1, which means that a has to be 1 over 20. So therefore, the particular solution is going to be yp is equals to 1 over 20 e to the 3x. Therefore, the general solution, so the general solution, which we're just going to call it y, is going to be equals to this part, which is C1 e to the minus 2x plus E2 e to the minus x, which is the homogeneous solution, this part, plus the particular, which would be 1 over 20 e to the 3x. And this is the solution. Now, it is very, very important to notice that the particular solution depends 100% on what this is. And in this section, we will deal only with three kinds of functions: exponential, polynomials, or sine and cosine. If you try to use more sophisticated functions here, like tangent or cotangent or something else, this method doesn't work. So we need to figure out a different way. But for now, we will focus on three cases only. This will be either exponential, a polynomial, or a sine or cosine. All right, so let's try the second example. Notice that the left side is the same, which means the homogeneous solution is going to be the same one that we already got. Remember, the homogeneous will be C1 e to the minus 2x plus E2 e to the minus x, because we did that one for the previous one. Now for the particular, since the function f of x is now a polynomial, in this case it's a binomial, then the particular solution will be ax plus b. If this one was x squared, then the particular solution will be ax squared plus bx plus c and so forth. Okay? And then we do the exact same thing within the previous one. Just take derivative, so y prime will be a, and y double prime will be 0. So again, if we plug it in here, we're going to have 0 plus 3a plus 2 times ax plus b should be equals to x plus 1. Okay. Which if you distribute, you will have 2a, 3a. If you distribute this, we're going to end up with 2b. So the first equation is going to be 3a plus 3b. This is the coefficients, so they should match this one. So they should be 1. And then the 2ax should match this one. Okay, that's what I mean. So this should match this. And this should match that one. So therefore that means that 2a should equals to 1. So that means that a is equals to 1/2. And then if you solve for b, then you should check this. This is just basic algebra. B is actually equals to minus 1/4, I think. So you should just check these values. So therefore the particular solution y of p should be 1/2 x minus 1/4. Okay. So hence the general solution. So the general solution should be y is equals to c1 e to the minus 2x plus c2 e to the minus x plus 1/2 x minus 1/4. So this is the general solution. And that's it for that part. Now, I told you that this is easy, but it can be, or it can get very, very annoying. And this is what I mean by very, very annoying. Okay. So let me make a note here. Let's say that the equation look like this instead. Okay, so if, it's a big if. So let's say that the equation was y double prime plus 3y prime plus 2y, but now this was just equals to like x e to the 4x. Now, because of this, then the particular solution will need to have this form. Well, it needs to have e to the 4x to accommodate this part, but because of the x, you're gonna need the polynomial version, so this should be ax plus b. And now you can see if you're taking derivatives of this, it's gonna be now more annoying because you need to use the product rule, and therefore it will take longer, but the process is identical. You just have to find y prime, y double prime, plug it in, and make sure that the coefficients match, and that's it. However, that's gonna be more annoying and it's gonna take longer. Alright, so now let's do an example where the right side, or f of x, now is a function that depends on sine or cosine or both. So remember, we already know that the homogeneous solution is equals to c1 e to the minus 2x plus c2 e to the minus x, okay? Because this is still the same. Now the particular solution is going to look like this. It's going to be a sine 3t plus b cosine 3t. Okay. And like I told you before, just take the derivatives. So y prime is going to be 3a cosine 3t minus 3b sine 3t. And then y double prime is going to be minus 9a sine 3t. And this will be minus 9b cosine 3t. Alright, so next, just plug it in here. Okay, so I'm going to plug it in like we did before. So we're going to have minus 9a sine 3t minus 9b cosine 3t. And then plus 3 times 3a cosine 3t minus 3b sine 3t, and then plus 2 times y, which is just a sine 3t plus b cosine 3t, and this has to equals to sine 3t plus cosine 3t. Well, I changed everything to t, okay, so let me just make this t. It doesn't matter, to make life easier. Okay, and this will be now t. It doesn't really matter. Okay? All right, so then from here you need to distribute. Now before we distribute and combine like terms, let's just make sure that you follow what's going on here. So y double prime is this, which is exactly this part. Then y prime will be this, and then just y by itself will be this. Okay, So remember, we're trying to show that it's equal to the other side. So we want this to be equal, okay? So you have on the left side sine and cosine. On the right side you also have sine and cosine. So if you distribute and combine like terms, so on the left side, so from the left hand side, so if you factor sine 3t, so you can see from here you're going to get minus 9a. Then if you distribute from here, you're going to get minus 9b. And then from this part, you're going to get 2a. Okay? And this has to equals to just sine t. So therefore, this means the minus 7a, you combine this and this, minus 9b has to equals to 1. So this is on the right hand side. Then if you look to cosine 3t, then if we do the same thing we did for this one, we will end up with minus 9b plus 9a plus 2b, which this has to equals to cosine 3t, so there should be 3 in here. Then this implies that 9a minus 7b should equals to 1. So then you have this system of equations, which is minus 7a minus 9b should be equals to 1, and then 9a minus 7b should be equals to 1. Now if you solve this, you should check this by using basic elimination. This is minus 7 over 130, and b is minus 9 over 130. Again, you should check that this is the case. Therefore, the particular solution, so particular solution will be minus 7 over 130 sine 3t plus or minus actually 9 over 130 cosine 3t. Okay, so therefore the general solution, again, you need to have both of them. So the general solution will be y. It will be now c1 e to the minus 2t plus c2 e to the minus t. Remember, I changed from x to t. And then minus 7 over 130 sine 3t minus 9 over 130 cosine 3t. And this is the solution. All right, before we finish this example, let me tell you one thing that you should be careful about. So note, so let's say that you have y prime plus 3y prime, so it should be double prime, plus 2y, but let's say that this was equals to only sine 3t, okay? If this was the case, the particular solution still has to be like this: a cosine 3t plus b sine 3t. So you still need to add both of them, sine and cosine. If the right side has sine or cosine, the reason why you need both of them is because remember the derivative of cosine is sine, and the derivative of cosine is minus sine, and the derivative of sine is cosine. So you need to include both of them, even if this one only has 1. And the difference is once you equate the coefficients, well, whatever you get here, like in this case, it will have to equals to 1, and then the second part will have to equals to 0, and that's it, okay? But a very common mistake people do is that if they see sign here, then they will use this part, and will give you the wrong answer, okay? So make sure you use both of them, even if this one only has 1. All right, let's do one last example, and this one is very interesting and important for this reason. Look, before we actually solve the problem, let's say that the equation you're trying to solve was this, okay? If this was the case, then the particular solution will be r squared minus 1 equals to 0, which implies that r1 is equals to 1 and r2 is equals to -1, right? So then the homogeneous solution will be c1 e to the x plus c2 e to the minus x, okay? Then the particular solution, in this case, it will be a cosine x plus b sine x, like I just told you in the previous page, and then you just keep going, okay? Now, if you look to the problem we're trying to solve, something very interesting is going to happen, and if you don't notice that, you're never going to get the question right. So here it is. From here, the homogeneous solution, okay, we're going to have r squared plus 1 is equals to 0, which means that r is equals to plus or minus I. And notice that these are complex. So therefore, the characteristic equation is going to be c1 cosine x plus c2 sine x, because the imaginary part is, the real part is 0. Now this is a big problem because the homogeneous solution is going to match the particular solution. Whenever this happens, that's a big issue and you need to fix it, and to fix it, it should be pretty simple. So notice that if we didn't have this, if the homogeneous solution wasn't this, then the particular solution is supposed to look like this. But since this matches this, that's a problem. So therefore, the particular solution is going to be t, so you're going to multiply everything by t, and the rest is going to be the same. In this case, actually not t, x. So you're going to multiply everything by x. And you can think of this like if you have a repeated solution, so you multiply by x. And this is going to make taking the derivatives much messier. So this is what I mean. So here, if you find the first derivative, now you have a product. So you have this times this. So the derivative of the first one is 1 times the second one plus the first one times the derivative of the second one. But the derivative of the second one is going to be now minus a sine x plus b cosine x. So therefore, the second derivative is going to be now minus a sine x plus b cosine x. So this, the derivative of this will give you this. And now you need to figure out this derivative, in which we had to use the product rule again. So it will be the derivative of the first one, which will be 1 times the second one, plus the first one, which is just x, times the derivative of the second one, which would be minus a cosine x minus b sine x. So if we plug it into the equation, so we plug in again, and we simplify this, we will have minus 2a sine x plus 2b cosine x, and then you're going to have minus ax cosine x minus bx sine x. So this is just y double prime, and then plus y prime, which plus y, which the particular solution is this one, so that will be a x cosine x plus bx sine x, and we want all of these to just equals to cosine x. Now notice here that this will cancel this, and this will cancel that. So therefore from here we have that minus 2a, which is the coefficient of sine, has to equals to 0. So that means a has to be 0. But 2b, which is the cosine of, the coefficient of cosine, has to equals to 1. So that means that b is equals to 1 half. So therefore the particular solution is going to be x times a, which is 0, plus b, which is 1 half sine x, which will be equals to x over 2 sine x. Therefore the general solution will be y of x. It should be the homogeneous, which is c1 cosine x plus c2 sine x, plus the particular, which will be x over 2 times sine x. And that's it. Okay. So the moral of this problem is that if the particular matches the homogeneous, then you had to modify the particular. Okay.